First of all, I want to thank the department as well as the organizers of this talk. In particular, I would like to thank my niece's daughter who wanted me to give a talk connected with game theory. See, the topic that I have chosen today to discuss among the students is simply a problem which was discussed in Talmud, which was written some 2000 years ago in the language of Hebrew actually. I'm going to write down some figure and you can try to see whether you can see any rationale behind such a figure. The problem is simply the following. There is a king who has 3 wives in his harem, and suddenly he dies and he leaves an estate. It is worth something, I will write it about it. And then each one of the wives claims some part of the estate. If the total amount claimed by the 3 wives is less than or equal to the value of the estate, then there is no problem. Each one will be given what they have asked for. But the real problem is the value of the estate is strictly less than the amount claimed by the 3 wives. Now let me write out some numbers, and these are the numbers which are taken from Talmud. I have to tell you that. So the discussion from the game theoretic point of view was carried out by 2 well-known game theorists. One of them is unfortunately no more, he is not alive. The other one is a Nobel laureate in economics. The person who is still alive and gives some beautiful expository lectures is Robert J. Aumann. He is a professor in the Department of Mathematics at the Hebrew University. The other person who is no longer alive is Michael Marshall, who is the great expositor, I should say. So from the game theoretic point of view, it is discussed in a very beautiful paper by Aumann and Marshall. This is the paper I am referring to, or J. Aumann and Michael Marshall. The paper appeared around 1983 in Journal of Economic Theory. So I'm going to write down some numbers. You can see these numbers without any problem. D1 is the amount which is claimed by the first wife, which is 100 units of money. D2 is 200 and D3 is 300. Here I am going to write down the estate, worth of the estate. If the worth of the estate is 100 units, each one is given equally. 33 1/3, 33 1/3, 33 1/3. This is the amount given to each one of the wives. If the value of the estate is 200, the first one gets 50 units, the second one gets 75, the third one gets 75. If it is 300, it is 50, 100, 150. If it is 400, it is 50, it is 125 and 225. So these are the numbers which is taken from Talmud, remember. And what is the rationale behind these numbers? How did they come up with these numbers? What is the reason? It's not clear, at that point of time, how they manage this. And in the same Talmud, there is also another problem which was discussed. It is called the garment problem. There was a garment which is worth something like 10,000 pounds. And there are 2 claimants to the garment. One of them says the whole amount should come to her. Yeah, The other one claims half of that should come. Let me repeat. The worth of the garment is 10,000 pounds. One of them says the entire amount should come to her. The other one says half of that should come. How do you divide this 10,000? The answer given in Talmud is the following. The person who claims a whole, she gets 7,500 pounds. The other one gets 2,500 pounds. What is the rationale behind it? See, the first one says the entire amount should come to her. The second one says half of that should come. See, I can explain what is known as the garment principle briefly. See, what you have to do is, you have to divide this 10,000 into two parts, x1 and x2. Okay? Where x1 is what the first one gets and x2 is what the second one gets. Of course, there are several ways of doing it. For example, the first one can get 8,000, the second one can get 2,000. That is one possibility. Or the first one can get 6,000, the other one can get 4,000. But then remember, the first one says the entire amount should come to her. The second one says half of the amount. But then the solution is given like this. So let's say the amount demanded by, this is D1, D1 is 10,000. That's what she demands, the first one. The second one claims half of that, that is 5,000. Okay? The problem is, this is the value of the garment, and the first claimant claims the whole thing, the second one claims half of that. Now I am going to tell you the garment principle. The garment principle is the following. Let's look at x1. And let me write x2 also. See, what is claimed by D2 is 5,000. So out of 10,000, remove this 5,000. So you give it to the first one. Is it clear what I am saying? That is, the first one claims the whole thing, the second one claims only 5,000. So since she is claiming only 5,000, give the rest of the 5,000 to her. 5,000. And similarly, since this one is claiming the entire amount, so when I subtract from this, it is 0. Okay? Now, what is remaining is 5,000. Divide equally. 2,500, 2,500. This plus this, 2,500 plus this. So this is the mathematics behind it. And that's what they have followed here. So this is what is called the garment principle, which is discussed in Talmud. So it's very interesting, I mean, the way they have analyzed this problem. So let me write it mathematically in a better way. So let me say E is the value of the total amount, and D1 is some amount which I am not going to specify, and D2 is some amount which I am not going to specify. This is claimed by the first one, D2 is what is claimed by the second one. And the problem is really interesting only when D1 plus D2 is bigger than E. Because if D1 plus D2 is less than or equal to E, there is no problem. Because you can give the first one to D1 and D2. So such a problem is what is called bankruptcy problem. When there are n claimants, D1, D2, Dn, and the total Di is less than the estate, then that problem is called bankruptcy problem. Okay, so that's precisely what they are. And I also now I'm going to give you the principle behind this. I'm going to assume E, and there are only two persons, and first one says D1 should come to her, should come, the second one claims D2. So how to divide this without the numbers? I'm going to do this. Let me introduce a notation. For any real number A, what I mean by A plus is maximum of A comma 0. If A is positive, A plus is A. If A is less than or equal to 0, A plus is 0. Okay? With that understanding, I am going to write down the numbers x1 and x2 with reference to the number E. and E is strictly less than D1 plus D2. That's the situation. Okay? Alright. So let me write out. X1 is what the first one gets, and X2 is what the second one gets. This is. Now, the second one is claiming D2. So from E, you subtract D2. Whatever remains, you give it to this. That is the first thing. E minus D2 plus, of course. And similarly, D1 is what the first one claims. So E minus D1, whatever remains, you give it to this. Now from E, subtract these two numbers and divide equally. Okay? Is that clear what I am saying? That is, from E, subtract these two numbers. This could be 0 or this also could be 0. That is irrelevant. But whatever it is greater than or equal to 0. This is also greater than or equal to 0. From E, subtract these two numbers and then divide equally between these two. So the first one gets E minus the sum of these two divided by 2 plus this. The second one gets E minus the sum of these two divided by 2. So x1 is simply E minus the sum of these two divided by 2 plus this, and x2 is E minus the sum of these two numbers divided by 2 plus this. And this is what is called the Garment principle. Okay? So here what they have done is the Garment principle. Because you can divide, for example, if the total value is 100, you can divide in infinitely many ways so that the sum adds up to 100. For example, you can give 20, 40, 40. That is one way of doing it. Or you can say 30, 40, 30. There are infinitely many ways of doing it. But then if it is 100, it is simply give to each one of them equally. If it is 200, give the first one 50, the second one 75, the third one 75. If it is 300, give 50 to the first, like that. So when it is 400, see, you can see, once it is 200, the first one is getting only 50-50. Whereas for them, it is increasing. What is the rationale behind? It's clear. What they say is, the loss for the first one is 50, because this person claims only 100. So 100 minus 50, 50. So until the loss comes to 50, these two will really get increasing thing. Until then, the first one will get 50. So that is the rationale behind it. And now this, I mean, can you do it in some other way so that it will be similar? No, you can't do it. Here, I have defined the notion of Garment principle when there are two contestants. But here there are three. So how do you do that? It is very simple. What you do is, you take any 2 by 2. For example, how this comes about is 50 plus 75, 125. Write E as 125 and D1 as 100 and D2 as 200, and follow this principle, you will get 50, 75. And similarly, 75 plus 75, you add 150 rupees. Take the worth as 150 and use the Garment principle. Here it is 200, it's 3. Let me do it at least one example. Okay, let me take this. For example, I am taking the second and the third. What is the sum of these two? The sum of these two is 150. I have to divide this 150. And what is D1? D1 is 200 and D2 is 300. Okay, I have to use the Garment principle and get it. So let me write x1, x2. I'm sorry, here I should say D2, D3. D2, D3. X2 and x3. Okay, the second and third. Okay, now, see, this person claims 300. So 150 minus 300 is a negative number, so it is 0. And similarly, here 150 minus 200, so it is 0, 0, that part. So simply divide this into two parts, 75, 75, that's what it is. So if you take any 2 by 2, it follows the Garment principle. That's the best part of this story. And such a solution is what is called a consistent solution. Because you can write it, and can there be more than one consistent solution? That is the question you would like to ask. No, there is only one consistent solution. That is, if I take any 2 by 2 and if I follow the Garment principle, then these are the numbers, and that will be given in a unique fashion. Okay, so that's the principle which Talmud, some 2000 years back, they followed. Talmud is something like Bible or whatever it is. It discusses various problems, religious problems and problems of this type, criminal problems. Many things are discussed in this, which is written some 2000 years back. At that time, they don't have any knowledge of game theory, but they have some kind of a logic here, which follow. Now, what Aumann and Marshall do is, they took up these numbers and formulate this problem into a game problem. The way they formulate is what is called, familiarly known as cooperative game theory, which was developed by von Neumann and Morgenstern. The first book on game theory came in 1947, but of course it has gone through several editions, and even in paperback it is available now. So that is the thing which they follow. And once you formulate the cooperative game theory, there are several solution concepts which were discussed in the literature. Von Neumann and Morgenstern discuss what is known as the stability solution. But unfortunately, there are games in the cooperative game theory which doesn't have a solution in their sense. There is also another solution concept which was introduced by, I think it is attributed to Gillis, who wrote a PhD thesis in 1955 in Princeton. But core also need not exist in general. But there was another solution concept which was discussed in an axiomatic fashion by Lloyd Shapley. That always exists if the game satisfies certain axiom. That is what is called the Shapley value. In fact, many of the economists use that. There is yet another one which is being used in the literature, that is called the nucleolus. And it is again a unique numbers which will give to each one of the players. I will discuss a little bit about nucleolus and things like that later. First, let me give you a brief introduction to cooperative game theory. Okay. So remember these numbers. I'm going to erase it because I don't have a big board to keep it as it is. Okay. So let me erase this. How many minutes do you have? Can you tell me? So this is an introduction to cooperative game theory as developed by John von Neumann and Oscar Morgenstern. They wrote the first book on game theory. It's called Theory of Games and Economic Behavior. Okay, there are n players. Just for the moment you forget about this bankruptcy problem. There are n players. N is equal to 1 to n. N could be 3, n could be 4. In this particular problem there are 3 players, 3 credits. Okay. Now, any subset of S is called a coalition. I mean, this is the usual way of understanding. Any subset of N is called a coalition, and if I take the entire player set, it is called the grand coalition. I mean, these are terms which most of you will know. So this is called a coalition. And if it is N, it is called grand coalition. Okay. Now, I am going to associate with each as a real number. That real number tells the worth of that particular coalition. Okay. For each S, V of S is a real number which is the worth of that particular coalition. Okay, is that clear? Okay. Now what do you do with this? I mean, this N together with this V is called an n-person game in cooperative games as discussed in n together with v. Usually we take v of s is a number between 0 and 1 without loss of gender. There is no loss. One can easily show that. Okay, so don't worry about that. Now what do you do with this? That's the question. Okay, let me give you an example so that you will understand what I am trying to say. Take n is equal to 1, 2, 3. Let me erase this. Example. V of I, any individual player I is 0, and I will also define V of the empty set without any player is also 0, and V of 1, 2, 3 grand correlation is 1, and V of 1, 2 is also 1, and V of 2, 3 is also 1, and V of 1, 3 is also 1. I have defined for all subsets of this. So these are the worth of the correlation. That is, in other words, if 1 and 2 join together, they can make 1 units of money. If 2 and 3 do it, same thing. You all of them do. It is, I mean, this is something like a voting game. Either, out of 3 players, if 2 of them support some rule, then that rule is passed. So this function takes only 2 values, either 0 or 1. 0 means it is a losing coalition, 1 means it is a winning coalition. So that's what it is. It's a voting game, essentially. In Parliament you can see it because there are 534 members and each one of them you can regard that as a player, and if any law is to be passed, either at least half of them should support depending on the law or whatever it is. So that's what I am saying. This is a voting game. Okay. This is a simple example. Okay. Alright. Now, as I already mentioned, the point is they define the notion of a stable set. See, if I have to define it, it takes too much time, it is technical, and I won't go into that. But let me say, what are the solution concepts with this? That is, in other words, suppose the grand coalition is formed, then how do you divide this 1 unit of money? That is one of the problems which business people would be interested. Suppose there are n companies, each one of them is competing with each other, whatever it is, and if they join together, they make this, and you have to divide them. What is the best way to do it? So that's the problem which Fonneman and Morgenstern wanted to discuss, and they give a solution, but unfortunately that solution may not exist in general. That's what precisely. They have given several, for example, for such problems, stable sets exist in the sense of Fonneman and Morgenstern. For example, anyway, I don't want to get into it. So stable sets. Set. That is the notion of Fonneman and Morgenstern. 2, core of the game. See, if something is given to each one of the players, nobody can object. Such an element is called a core. And no coalition also cannot object. But unfortunately, such a thing may not exist in a given game. Let me repeat. This is a very nice concept. In many market games, this core turns out to be non-empty. For example, in particular for those of you who are doing mathematical economics, you will be studying market games and you will be able to show that core is non-empty in such games. That is, that is, you divide this 1 unit of money into 3 parts so that when it is given to you, you cannot object to that by any method. And also no coalition can also do it. That is, 1 and together also cannot object. Such an element, such a division is possible. Then we say core is non-empty. But unfortunately, core can be empty. In particular, in this game, core is empty. You can't divide it. You can't divide one in such a way such that it satisfies those properties. The third property is due to Shapley. That's called Shapley value. There is a very nice concept in the sense that in his PhD thesis, because see, when Fonneman and Morgenstern wrote the book in 1947, they asked the fundamental question whether every n% game has a stable set. That was not answered until 1967 or 64 or 65, and Lucas came up with a 10% example where there is no stable set. Okay, and what Shapley did was, in order to avoid the ambiguity in the problem, he write down certain axioms for the cooperative game theory. And if you follow those axioms, then there is a number, specific numbers for each one of the players. And that is what is called the Shapley value. This exists. Okay, this exists. The fourth concept is what is called nucleolus. This also exists, and this concept was introduced by David Smidler and written around 1964 in Management Science. That paper appeared in Management Science. He is a student of Robert Aumann. Robert Aumann. See, here I have to tell you, I forgot to mention that Shapley is another famous game theorist. He is no more, who also got the Nobel Prize in economics for certain problem which has lot of practical applications. That's called the matching problem. Okay, I am not discussing it at the moment. So Smidler discusses nucleolus. I mean, what is nucleolus? Nucleolus is, in a certain sense, a minimal element in a collection of elements. That is the view of that. The point is, nucleolus is unique. It has a unique element. Now, what Aumann and Marshall, in their paper which appeared in Journal of Economic Theory, the Talmud problem, the numbers which they give is simply nothing but nucleolus of a game which you formulate there. So I am going to give you the formulation of Aumann and Marshall, and then say the numbers which they give is nucleolus. Okay, because again, to define it technically, it's not difficult, but it takes too much time. So I will avoid that, but then say the solution which is given by Talmud coincides with the nucleolus concept developed by Schmeidler. Those of you who are interested can see the original paper as well as the paper of Aumann and Marshall to understand what you mean by nucleolus. Okay, so let me just write down. So let's take the claimants. So these are the D1, D2, Dn, and we assume D1 plus D2 plus Dn is strictly greater than E, because that is when the problem is interesting. Such a problem is called a bankruptcy problem. What is the solution? The solution is simply divide E into n parts, non-negative, such that their sum added to E. Such a thing is called a solution. What is a consistent solution? First of all, it has to be a solution, non-negative, and then the sum added to 1. But then, if you add any 2 by 2, it should follow the Gorman principle, and you are going to get something that should coincide with X. For example, so let me write consistent solution. x1, x2, xn, that is, you give x1 to the first one, x2 to the second, xn to the, it's called a consistent solution. 1, if xi's are non-negative and summation xi equal to E, because that's all what you have at your disposal. You have to divide this among the n participants. So this is the thing. This is called a solution. There is one more condition which makes it a consistent solution. What I mean by a consistent solution is the following. You take any 2 by 2, I not equal to j. For example, you can take 1 and 2. Okay? So, for example, 1 not equal to 2. I will do it for this, same thing for all I and j. So, for 1 not equal to 2, take E and E12 as x1 plus x2. Okay? and then you write D1 and D2. D1 is given, D2 is given. Now look at this problem. Now it is a two-player problem. Use this is your total worth, and then use the Garment principle. The Garment, I'm using the notation exponential. The Garment principle may give you the solution y1 and y2. Need not be exponential, okay? If it is to be consistent solution, x1 must coincide with y1, x2 must coincide with y2. So that's what is happening here. If I take 2 and 3, what I do is I add x2 and x3 and d2, d3 and use the Garment principle. That will give you y2 and y3. x2 must coincide with y2 and x3 should coincide with y3. So such a vector is called a consistent solution. In fact, the vector which is given by the Talmud is everything is a consistent solution. You can check it. Now the question is the consistent solution unique? Yes. There cannot be more than one consistent solution. Because in the Talmud problem, if you increase the value of the estate, each one will get more than what is given before. It is an increasing function. x1 is a function of the E and x2 is a function of E. It is increasing with reference to E. If E increases, x1E and x2E simultaneously increase. So because of that, you can check. Uniqueness is not a problem. To show that there is a consistent solution is not difficult. You can just follow the argument which is given. That's a very easy argument. You don't need any game theory to understand the existence of a consistent solution. You need to know game theory to connect it with nucleolus. Okay, so let me now give you. Alright. So the game problem is the following. I think I still have some minutes, right? Alright. So now the players are these players. 1, 2, N. E is associated with this. This is the one. D2 is the claimant, etc. Now, I am going to define a game, cooperative game, with the help of the data which I have. Alright, so let me write V of the grand coalition, that is this one. This is what is available to me. This is what all of them together is going to get. They can't get more than that. Alright? Okay. Let S be a subset of here. Yeah. Now define V of S equal to E minus summation di I belonging to S complement. That is, you leave out the players who are in S from the N players. Okay, add whatever they claim and define the plus of this. If it is negative, 0. If it is positive, take that. So I have defined it. Is that clear? That is, S is any coalition. So for example, S is 1, 2. Then E minus D2 plus D3 plus Dn plus. I already told you the number A plus is simply maximum of A and 0. Okay, so these are non-negative numbers. So this is how we define for any S. And V of N is E. I will give an example, simple example. Okay, so this is what it is. So the nucleolus associated with this game is precisely the consistent solution given by Talmud. Okay, so that is the theorem. So let me write down the theorem and then give an example. Main theorem. Talmud's consistent solution is nothing but nucleolus of the cooperative game. So this is how the game theory comes into play. Of course, at that time, game theory was not existing. So they were able to identify. So it's a beautiful result in the sense that how they thought about it, that is beyond our comprehension. But that is precisely what is happening here. Okay, now let me give you an example. Okay, example. Let me erase this. So let me take n is equal to 1, 2, 3 as in the Talmud's example, and D1 is 100, D2 is 200, D3 is 300. Okay. Here, what is V of 1? V of 1 is, what is the state? I have to give you some number for E. Say E is say 200. Let me take 200. That example. V of 1 is 200 minus, what is the complement of this? 2 and 3. D2 plus D3 is 500 plus, which is 0. Here is a negative number, so it is 0. V2 is 200 minus D1 plus D3. D1 plus D3 is 400 plus, which is 0. What is V3? V3 is 200 minus 1 and 2, 300. Again it is 0. So all the single player coalition gets 0. The worth of that is 0. They are not going to do anything. By standing alone, you are not going to achieve anything. So that's what it is. Okay, now I have to go to the 2% coalition. V of 1, 2 is 200. The complement of this is player 3. D3 is 300 plus, which is 0. So this coalition, 1 and 2 joined together is not going to help. What is V of 1, 3? V of 1, 3 is 200 minus V of 2, because the complement of this is 2. 2 is 200. Which is 0, of course. I don't write anything. And V of 2, 3 is 200 minus 100, because the complement of this is 1, it is 100. So this is equal to 100. So this is the game. I have formulated the game. Okay, this is precisely the game. And the nucleolus I have not defined because it's technical and thing, but that gives a unique number by which the players will be given. Okay, so that's precisely the concept. Nucleolus given by Schmeidler coincides with the consistent solution given by Talmud. Okay, now let me give you a brief, reference to all these things. And if you have any question, I would be happy to answer later. But there is a vast literature which is, there is the first paper, but there are several papers written. In fact, I can give you one instance where this can be usefully applied. For example, in sharing Kaveri water, I think essentially there are 3 states involved, if I am not wrong. Karnataka, Tamil Nadu and Maharashtra, perhaps. Or I don't know, Andhra, I am not sure. Kerala maybe to some extent, or Puducherry, whatever it is. Okay, 5 players, okay. So each one is going to claim certain amount of water. So D1 is what is claimed by Karnataka, they will claim the maximum, and Tamil Nadu is the next one, and Maharashtra will claim D3, D4, D5. Perhaps one can follow this principle. And it will be a very fair principle, I would say. So one can, there are many other practical use of this. Sharing of electricity is another thing where one can use this. There are many ways of using this concept of consistent solution, which is easy. Of course, to understand that it is equivalent to nucleolus, that is purely a game theoretic thing. But this problem has practical use, that's what I'm saying. So let me give you briefly some references. The first reference is the book by von Neumann and Morgenstern. (1947), first edition, Princeton University Press. Theory of Games and Economic Behavior, that is the title. 2. The paper that I am referring to is JET, Journal of Economic Theory, 1983. Aman and these are the authors. Master. And since I spoke about nucleolus, the paper by David Schmeidler, 1964. David Schmeidler. Which appeared in the Siam Journal of Management Science or whatever it is, you can check it. And he is a student of Aman. Aman is a Nobel laureate and he is no more. And both of them are not alive. But this is the first book on the subject game theory. And there are many other applications of game theory, but I don't have time to discuss, but I'll stop here. Did I